Well, I'm glad everybody could make it here today. I'm Alex Brikoff, and I'll be hosting this clinic tonight. This is the October 2020 edition of the Eastside Get Together Clinic. And as always, our clinic tonight is sponsored by the 4th Division of the Pacific Northwest region of the National Model Railroad Association. So tonight's clinic will be presented by Max Maginness, and the clinic is titled Wiring for DCC. Max will be giving a short history of DCC as based on the standards of today. These standards have evolved from the original DCC concept nearly a quarter century ago. The clinic will also give a refresher overview of the basics of some of the nuts and bolts of wiring your layout for DCC. Max will conclude with a short discussion about DCC operations that might be a bit mysterious to some people. So Max, it's all yours.
Okay, thank you, Alex. I've put down the bottom here as a practical guide. It's what they called the first one as an update. It actually was given, among other earlier things, at the NMRA convention here in 2004, which Dee will remember extremely well. So at that point, we were up to several versions already, and this one's a big update on that. Of course, there's been a lot of technical elaboration in DCC since then, but most of the basic stuff and the standards that apply have very much stayed the same. So we're able to build from those. All right, so the little background that Alex mentioned, the semi-official, if you like, standards announcement was 27 years ago, right after the NMRA convention that year. It was obviously within the NMRA, but the announcement was made in the Model Railroader that year. Down the bottom left on here, there's a very idealized waveform for the DCC. That's not quite how it works in practice, but the basic arrangement has stayed the same. But anyway, 10 years later, when I was looking at this original clinic, there was this lovely comment in the NMRA bulletin about people hearing DCC and cringing. So that's what led to the earlier version of this clinic. The theme at the time was, it really is less complicated, well, than DC cab wiring. And there was a book came out from Kahnblack about that time, which this picture in the bottom right came from, and said, you will save all of this wire by going to DCC compared to cab wiring, if anyone remembers that. That didn't turn out to be quite true, but it was a good pitch at the time. So coming up to date a little bit more, obviously the legacy DC layouts persist. There's still quite a few people who haven't converted or for various reasons can't. And I noticed the current Achievement Program Electrical still includes a considerable DC cab control and such items as electronic throttles, which were very popular with DC. So they're around. But I'm assuming in this clinic that just about everyone has at least a basic DCC understanding. You've either converted, you are converting, or you're doing a new layout, or you have one that's been in place for a while that you continue to improve. What I'll cover, Alex has already summarized this, but just a refresher on the DCC wiring, nuts and bolts if you like, or wiring connectors, perhaps in this case, and how to best use them, and a few reminders on common track features. But the item I wanted to spend about half the clinic on is what I call points of confusion. These are misunderstandings, myths, legends, and all sorts of similar reasons why various items associated with DCC seem to continue to cause confusion. And this shows up periodically on the various chat groups and similar, where the same questions keep coming up. And then there's a whole flurry, goes on and on for a couple of weeks, and then the moderators cut it off. and it goes away, and then a few months later it turns up again. So we might talk about some of those. What I'm not going to talk about is the basic theory of DCC. That could go on forever, or how to install decoders. That was quite an issue. Probably still is if you're trying to do an older locomotive, but it's become much more easy to do, or programming them. JMRI, the Java Model Railroad Interface method of software for doing this, has now been around almost as long as DCC. It's very much easier, and if you never programmed anything beyond the lights in a non-sound decoder, maybe you don't need it, but beyond that, you'll drive yourself crazy without it. So my only comment about that is load it on your laptop and use it. I'm not going to particularly talk about competitive equipment either. That's become a bit passe. And I'm not going to wire your layout, even for generous rewards. I've called it a medium-sized layout. Later on, I'll talk a little bit about what that sort of means. It's typical, or maybe a bit smaller than quite a few of you have. The basics, and these are common one way or another to all DCC systems. There's some form of command station that stores the addresses and the instructions for all of the locomotives and any other accessories you want to run, and the throttle, for want of a better term, which you're giving those instructions on, whether it's wirelessly or wired connected, doesn't really matter. And then a booster to bring those signals up to the full track power level. So then we get into the famous DCC bus wiring, which would typically parallel the main track runs in the layout. I've immediately put sort of 14 gauge wiring here as a hint, just to suggest that it needs to be pretty hefty wiring for some reasons we'll get into in a minute. Unlike the original DCC promotions, it's not a good idea just to connect all the track directly to that and say I'm done, because one short circuit anywhere on the layout will shut the entire thing down. That may be embarrassing if you have multiple operators to the person who did it, but it's not very helpful for your session. At the very least, breaking the layout into power districts or blocks with their individual circuit breakers is just about mandatory. I could say highly recommended, but it goes beyond that. They should typically be about the same size wire as the main DCC bus. No reason to make them lighter. Might be an idea to color code them differently so you can tell, but that's not affecting the electrical properties. They may be connected to the track, possibly via a block detector to tell if that block's occupied by a locomotive or a train, particularly if you want to get into layout control systems or signaling. That's optional, obviously, but it's a good idea to allow for being able to put those in when you're doing the original wiring. Between the subbus, the track fed by a given subbus, there will be gaps, of course, to the adjacent one. Otherwise, you wouldn't have achieved anything by way of isolating any shorts or similar issues. The preferable turnout construction for DCC is all metal. I think plastic frogs, or so-called insual frogs, are really a bit of an anachronism these days. They're very good for train sets, okay for DC, but it's really much better to have an all metal arrangement and switch the frog, whether you do it electromechanically with the switches on a tortoise machine or with an electronic frog juicer, doesn't really matter. It's a matter of convenience. The end result is the same. You'll notice that this entire assembly from here right through to beyond the frog is isolated from the rest of the turnout by little gaps here and up here. That means these parts of the track are permanently bonded to this, and these parts, including the switch, to this. So this gets around what used to be called DCC unfriendly turnouts. Again, getting to be a bit of an old hat term. And then the other thing that's one of the famous confusion items, at the end of a significant bus run, whether it's a sub or the main bus, doesn't really matter, it's kind of desirable to put what's has many names, but Snubber seems to have become the popular one. And we'll talk about whys and wherefores of that later. So this is by way of putting things in perspective overall. Of course, this can get more elaborate if the layout gets bigger. It could be more than one booster, it could be a lot more circuit breakers. There could be reversing loops with their own automatic reversers and turntables and so on. But most of the basic stuff is covered in this diagram. So we can identify some sort of minimum set of wiring that needs to be provided. Firstly, the track power bus, and thanks to the NMRA standards, the signal on that and the wiring needs and so forth really don't matter who made the DCC equipment. So as long as the manufacturer of the control station has followed the DCC waveform requirements. Strongly recommend power blocking or power districts and all but the very smallest layouts, just for reasons of not wanting somebody derailing to shut the whole thing down, or usually running through a turnout in the reverse direction, because no amount of automatic frog switching will take care of that. And then we talked about automatic reversing for return loops, turntables, and so on. This is another one that keeps coming out, but I'm only really going to mention it here. During the programming of your locomotives on the so-called main, on the main track, where other locomotives are sitting, is Russian roulette. You're sooner or later going to end up programming them all at once or deprogramming it. So I really would say an absolute minimum is to have a programming track physically separate from the main, so that a locomotive sitting on that programming track cannot creep and get onto the main line. Not just not programming on the main, but physically separating the programming track. An air gap, in other words, not just a switch. So the control bus, these do differ with manufacturers. The purpose, of course, is just to provide multiple outlets for plug-in cabs or radio transceivers. If you have multiple boosters, that same bus will be used to synchronize them together so that you can move from one power district to the next without glitches. The actual wiring used depends a bit on who made the equipment. Cat3 telephone cable, in other words, is pretty common, but it's not unique. One thing that may not be quite appreciated is the transmission speed in DCC of the signal is not very fast. So, I mean, if you want to use Cat5, Cat6, Ethernet cable, fine, but it's a massive overkill. So the next other item that's important, I think, even minimally, if you're going to have any sort of DCC controlled or powered even accessories, including turnout control, they really need to be on a separate bus. Whether it's just isolated by a circuit breaker or not, or a full booster, that doesn't really matter. But the point being that if some part of the layout gets shut down for a short, you don't want to disable the turnouts and things. It's also recommended that you probably ought to be running, say, 12 volts DC around the layout as well. It's particularly handy for any local control of turnouts for light signals and so on. Point being that it's a good idea to put the wiring in for these when you start, because not only do you want to minimize your time under the layout, as you get further into developing it, you'll probably get less and less enthused about being underneath, physically or mentally, one or the other, or both. This is a reminder, somewhat from the previous one, that why some of these things differ. With DC control, if you remember, there'd be one locomotive, or a couple together maybe, in a block, and that was it. So the amount of current needed was pretty low. The wiring was pretty skinny usually, and the amount of power available being somewhat low, it didn't really matter if there was a short circuit for a little bit of time. If the locomotive was gliding through a turnout and did it, it probably would recover without, and you'd hardly notice it. But with DCC, the amount of current available is way higher, and the wiring needs to really be able to accommodate this level of power that it can handle, that the machine can handle. Typically, there's at least 5 amps available. That's why I've said 14 AWG, American wire gauge. sort of referring in general to HO for the track bus wire. Maybe in a very small layout and 1 or 2 locomotives, you could get away with zip cord or something similar, but better to assume you're going to want to expand and plan for that, I think. One thing that we always have to keep reminding people is if there's no control over a short circuit in a DCC layout, there's as much power being pumped into that as a old technology, a incandescent 60-watt light bulb. You probably realize that old-fashioned 60-watt light bulbs put out about 1 watt of light equivalent to 59 watts of heat. So that's just by way of a warning. You can melt things on rolling stock and such like quite easily. That means the booster and the circuit breakers and/or must trip and shut down very fast. That makes it way less tolerant of any little shorts or track problems or glitches. Even more annoying, it'll reset the sound. But the good news is that those pulses of current are very good for activating auto reverses or for switching to frogs with the frog juices and so on. So it's a good thing, but those currents can be pretty high. And the frog juicers in particular, the usual ones are made to handle that. What this means is overall the electrical resistance has to be really low. So a short, no matter where it is on the layout, even if it's way out at the end of the wiring, must pull enough current to make that work. So this is the famous quarter test. You put a quarter across the track and the cutouts should trip immediately. If not, that energy is going somewhere, hitting the wire, things like this, which is not a good thing. So another thing I will emphasize is a bit more, how the wiring, pieces of wiring, the sections of wiring are connected together into the track is every bit as critical as the size of wire that you're using. It's not at all uncommon for connections to have much more resistance than the whole length of the wire. And they tend to be the failure points. That phenomena is common to most electronics. And this is no exception, just made worse by the fact we're dealing with rather high currents. So here's a example arrangement. I've reproduced up the top left here the little logo, if you like, from the wiring diagram further back. A big black spot to emphasize the joints need to be solid and what is called gas tight. In other words, they're so solid and tight that air cannot infiltrate between the metallic surfaces, because if it can, it'll carry moisture and eventually it'll corrode, or at least get a film on it that'll spoil the conductivity. So this is under the layout. The track itself is up top here somewhere with the feeds to it. This is an example all covered up, but the joints have been soldered, which is okay if you've got an open top bench work and haven't put any scenery in or anything, but it might get a bit tiresome later if you need to work underneath holding a hot soldering iron over your head. But nonetheless, it satisfies the solid and gas tight as long as it's reasonably well done. I would emphasize, though, that I've seen a lot of layouts where people take the track wires, strip a bit of insulation off this, wrap them around, and think they'll get around to soldering it later. Later sometimes never comes, so don't do that. The other thing is, once soldered, you really want to insulate them. It's all too easy to bump things later and cause short circuits, which can be very hard to track down. So the red and the blue wires, as on the diagram representing the track bus. Further down here, I have a pair of wires. It's a sub bus, if you like, for the accessory power. And down here, this is a typical bit of just flat telephone from the wall to the receiver. If you remember wired telephones, carrying the control bus. That's, in Digitrak's case, it's a 6-wire cable, just a telephone cable. The spacing between these wires is another famous discussion point, but that's solder joints. Well, that's okay. And another popular one that causes some problems is so-called suitcase connectors. They're insulation displacement connectors, even if you close them like a suitcase. They're a bit touchy. People swear by them and at them. Swearing at them frequently comes from fudging the wire size. In other words, you got a bargain lot on eBay and they must be good, but there's many sizes and they're quite critical as to the range of wire size that they will work properly with. That's what I mean by fudging. And if you do that, you'll have loose connections. So what the bottom left picture suggests is, okay, this particular one is okay for 14 gauge. It's not okay for 24 gauge going up the track. So we'll put another bit of wire in between and then use these butt connectors crimped on to join the two together. It's okay, it's a little bit cumbersome, but there's a problem with, obviously, with soldering or these, even if done properly. And I mentioned a suitable tool. You know what gas pliers are. The critical point being you can adjust them so the jaws close almost parallel. That's really critical to squeeze these together and not have them slip. You can get a proper tool for it if you like, but they're about $80, and that seems to what people are. Then they complain they don't get joints. But so I'm offering a usable compromise here. All right, so other connectors. It's all very well to have IDCs and soldering, but not just later, but definitely sooner. You're going to want to change things. You're going to want to do troubleshooting. And you can't easily do that once you've soldered or put the suitcase connectors on. Soldering again after the fact, unsoldering and redoing it reliably is a bit tough, especially under the layout. And you can't do anything with the suitcase connectors except cut them out and put in new ones. So there's a variety of methods for handling this, all screw type, mostly screw type connectors. These terminal blocks are very traditional. They certainly encourage neat wiring, so indicated over here. But I would say do not put the wire directly under the screw and turn it down. It will work loose. It does not qualify as so-called gas tight. So these examples have the wires with spade or ring connectors under the screws and then well tightened. That's a very positive joint. It's a little bit of work though. You've got to strip the wire, you've got to crimp it into this, and you've got to put it on here. So these blocks, sometimes they're known as Euro connectors, I guess because they've been used in house wiring in Europe for many, many years, but not so much here. You only need to strip the wire for these. They have two screws here and a metal block in the middle that you push the wire into from each end and tighten down. That's okay, but many of them have just the screws into the hole in the metal block. You really want to get one, so I'm not sure if you can see it here, but here there's a little tab, a flexible metal tab, and the screw presses down on that. So now you've got the wire clamped between a metal tab and the bottom of the hole, not just having the screw ground into it. That may be okay for large gauge solid wire, but it's not okay for stranded wire or for a small gauge. Just something to remember. You have to look carefully to make sure you're getting the ones with these. A little more recent introduction is called Wago connectors. Wago's company. These are, you strip the wire, you use your thumb or fingers to open these little levers. You push the wire in and you snap the lever down. It's very effective, no tools needed other than to strip the wire. You can get them in a variety of sizes and current ratings. They're very reusable, and that's not just for casual hobby use. They're intended to be for power wiring as well. The remarkable thing is that the same device will handle a very wide range of wire sizes. I'm not sure I'd entirely trust it at 28 gauge, these ones, but certainly going between 12 gauge bus and maybe 22 gauge wire up the track is very feasible. There's some end-to-end ones as well if you need to splice a bus. And it doesn't really care if it's solid or stranded wire, which is nice. Nor do most of these others, but except the ADCs. There are some intended for stranded wire, but if you don't use those, it's probably you're going to nick the wire badly with ones that are rated only for solid. And it's way worse if you're using a combination that's not quite right. So I'm not sure I could really recommend using stranded wire with IDC suitcase connectors. There's a range of these. This is a 222 series, but there's other ones as well. One thing I've noticed, now they're becoming more popular, there's quite a collection of knockoffs of these original German ones from the usual source. They're almost indistinguishable unless you read the blurb on Amazon really carefully for odd wording. I don't think, I mean, it's not going to be fatal in our case compared to doing house wiring, but be a little bit suspicious about the reliability of those at the moment. All right, so the last time I gave this, many years ago, there was another dozen slides or so of excruciatingly fine detail on other connectors, turnout wiring, DCC, etc., etc., track gaps in the track, reversing loops, and so on. There is now way more information, very well arranged, from books, magazines for traditional media, even including the NMRA magazine, and of course websites beyond all finding. In other words, there's many, many of them, private and very public ones. Two traditional media, paper books I'd recommend. This one by Larry Puckett, not Gary Puckett in this case. Most recent version being out a few years ago. And then there's a slightly older one by Mike Polgrove, specifically on DCC. If you want to buy one, my gold star goes to this one because it covers the DCC wiring very well. This one has more, of course, related, as the cover suggests, related to wiring the locomotives and so forth, which isn't the immediate topic of what we're talking about today. As an acknowledgement, I have used some images from these books in the presentation. And then there's websites. The one that's been around the most, the longest, is Wiring for DCC, very obvious. Because of its age, it's a bit chaotic to navigate, but well worth it. There's also a corresponding chat group on Groups.io. Yahoo Groups died this week, actually, I think, but it's moved. That's quite lively. It's where a lot of these controversies resurface every few months. Because there's a response sort of to just about everything that's asked and other stray information, it pretty much caters for any level of understanding, which is handy. So navigation's a bit frustrating, but the content is all there. And you can trace all sorts of previous methods of doing things on it as well, since it's been around for so long. Mark Gurries has run his website a bit less time. It's a little bit more, if I might say so, professional, and a lot of it's at a significantly more advanced level. It's way easier to follow, so there's offsets. That's a compensation. And then there's chat groups. I've happened to follow the NCE and Digitrax ones, but there are others. And there's all sorts of other somewhat helpful sites, DCC Wiki and so forth. Doesn't seem to be all that much used, but if you hunt around, you'll find many others that are very helpful for a scan, and you can always ask questions on them, and you'll get all sorts of replies, which, like so much stuff on media these days, needs a certain amount of discriminatory reading. Don't take everything for granted. Okay, so that's sort of short-circuiting a lot of what I used to say before, but I think it's better known and easier to access now anyway. For the second part then, I'd already mentioned a couple of times these chat groups and some of the, yeah, what I'll call outbreaks on a few choice topics that keep repeating. And every time they reappear, misunderstandings, excessive explanations, wrong explanations, and especially opinions are very frequent and often very lengthy. And there's a lot of anecdotes. In other words, people say, well, it worked for me for the last 10 years. What the hell you think you worry about this for? And okay, that's fine for them. But it emphasizes what I think is sort of the underlying reason why these topics keep coming up. Individual layouts, very much unique. I mean, that's the whole point. It's a artistic expression, the whole hobby as much as a technical one. So construction is different, the track configuration is different in arrangements, and on top of that, the wiring and the control systems are not only unique, but sometimes a bit bizarre. So it's not surprising that what seems to be causing grief for somebody, someone else has never had the slightest inclination that that's a problem. I think another thing that's come up the last 10 years probably, a lot of current users are sort of more into the information layers, if you like, and the control, layout control bus, exercises and automatic signaling, and maybe a little bit less familiar with the underlying hardware and basic control arrangements. There's also the factor that anyone who's sort of unconverted, as it were, from DC, the barrier to entry to DCC is getting higher every year. Sometimes it seems every month. So it can be way more intimidating than it might have been 10 or 15 years ago. So consequently, it gets put off. I think that's, from what I can see, looking at these messages sometimes, club layouts tend to be big, they tend to be historic, they tend to have a lot of members who really just want to go there socially and run a few of their old DC logos. So not only is the barrier to entry high technically, the social barrier may be even higher. But that is just a cause of what we're saying. I'm not suggesting any way to do it, to overcome it. So I picked a few of the more popular questions, FAQs if you like, and that's what the next few slides are about. So wire size still keeps popping up, maybe less so than it used to, because back when people were much more likely to be converting from DC layouts with skinny wiring, it was a bit confusing, not the least because there was a lot of helpful advice that says, oh, no problem, just set all your block switches to one cab and connect the DCC to that, you're done. All right, well, it would work, sort of. Maybe even okay, maybe even for a long time, but it was inherently a bad layout, wire size, wire routing, for reasons we'll look at in a minute. So, but now there's a lot more settled on what to do and why to do it and how to do it. So it's probably died away, but it comes up every now and again. So really what we're looking for with the DCC wiring is we don't want to lose too much voltage between the booster output terminals and the furthest away point on the track when there's a train way out there with as many locomotives drawing as much current as we expect we're going to require to be delivered. 5% is a bit arbitrary of loss, but a lot of decoders now have so-called back EMF, so they'll compensate for what would otherwise be a drop in the speed. Beyond that, it might get a bit flaky running the lights and the sound and so forth. So the second item, B, even way out there at the end of the layout, if there is a short, the current flow that's possible must trip the booster or the circuit breaker, or if you're using it for that, the frog juicer or a reversing loop switch, or you're really out of luck in terms of being able to operate the layout, quite apart from the damage that may occur. So that's really the more important requirement. So I put a little table in here. You can find similar ones in those books and elsewhere, but I did with a little different emphasis. Mostly they just say, well, if you've got a foot of 12 gauge wire, it's got so much resistance, and okay, that's nice, now what? I figured out for 60 feet of wire, which means it's, let's say, 30-foot length of bus, where one wire goes out, the other comes back, 60 feet in total. So the resistance of the various wire sizes is there for that length. So we can figure if you've got a big lash up of locomotives way out there, maybe it's taking 2 amps with the sound going and the lights on and lighted passenger cars and so on. One of the compensating factors over the years, of course, is that motors have become a lot more efficient, and so have lights with LED. So the maximum current draw taken by the locomotives now may be more settled by the sound level they're producing than the motor or the lights, as used to be the case. With 12 gauge out there, there'll be about 1.5% loss of voltage. 14, 2.3. If you use 16 gauge wire, which is probably okay for a smaller layout, you might lose about 4%. So it's getting a bit near the edge. This is why I mentioned 14 gauge before. Now below that I put 22 gauge, which is not an uncommon wire gauge to use for connection to from the bus wires to the track, to the rails. Sometimes a bit skinnier. But anyway, let's assume there's 3 feet of that, 18 inches from the bus to one rail and 18 inches back from the other rail to the other bus wire. So that will lose about another nearly another 1% total, which emphasizes, don't make them too long, but on the other hand, it's not critical. There's a subset of this question is, gee, should I be putting really heavy wires up the track? The answer is, well, if you want, but no need. It's a short length. It doesn't make much difference. Another famous question on that one is, what wire, I can't get the 12 gauge wire into the terminals on the booster, what should I do? Well, the answer is use thinner wire, keep it short, and then connect it to the bus. But anyway, then you can do another calculation which says, well, if the power source could deliver it and you short-circuited it through that resistance, how much current would flow, at least for a very short time? And there's never going to be 130 amps flowing for more than a fraction of a microsecond, perhaps, but it's just to give a relative number. And you see that comes down quite rapidly. The point being that if you have a 5 amp circuit breaker, even an electronic one, it's going to take 8 or so amps instantaneously to make it actually pull out. So if the resistance of the bus and the track circuit and the joints and everything gets too high, it won't trip, and then you have a problem, as we've discussed. So this table is just really more comparison than advice, if you like. It does not take into account how well the joints in the wiring are made. The other part of it that comes up is, well, what about the rails? They're all in parallel with this. Don't they reduce the resistance? Yeah, not much. Nickel silver is about 20 times more resistance than copper, so it doesn't make much difference. It's also the reason why the best advice is to be putting feeders to the track pretty often. Typically every 3 feet is recommended, but you can be a little casual about that number. Just don't make it too big. All right, so there's one topic, wire size. It seems basic, but it keeps coming up. Next one, type of wire. This one's a bit more subtle. It seems to have died away of late, but this was hotly contested for a while. Pretty simple, solid wire or stranded wire, both, whatever gauge you want to use. So the obvious characteristics are solid at your local hardware store is very available, but less expensive. We're just talking same wires you use for house wiring, the so-called conduit wire that's not got the plastic sheath on it. You can use it with all types of connectors, but it's definitely harder the string under the baseboard, being pretty inflexible. Stranded may cost a bit more, and as I said, better not to use it with suitcase connectors. It is flexible. That's a big help. So where all this fuss came about was somebody who's been addicted to audio niceties was aware that with solid wire at the higher frequencies, even with audio to some extent, reasonably including some DCC signal components, the current doesn't flow through the entire cross-section of the copper. It tends to crowd along the outside, and that outside layer that's conducting gets thinner and thinner as the frequency goes up. So therefore the thought was, well, gee, stranded wire has got a lot of little conductors, and the same effect on them isn't anywhere near so serious until you get to much, much higher frequencies at all. So it got to be said, stranded wire must be better because of that. It has less resistance at higher frequencies. Well, yeah, but the problem is that really only works if all the strands are individually insulated from each other in the cable. And if you want to get something like that, you can go to your local audio store and buy monster cable for speaker connections. That's what it is. There's an awful lot of stuff in the audio literature about incredibly subtle perceptions people have about the difference it makes to the sound they're listening to. So the technical effect's pretty simple. The misunderstanding has tended to be pretty profound. So really what I would say is don't fuss on this. Use whichever one you prefer. Just make sure you're doing good connections. They're very much more the point for keeping the resistance down. This one goes on and on. To twist or not to twist, that is the question. It's perennial. It keeps coming back all the time. It's a good point for keeping the pair of wires forming a main bus or a sub bus close together. It does reduce radiation. These things have high frequency currents flowing in them, and they create external radiation that can be picked up. It can interfere with your detection and your signal bus, the control bus and the signals. And it's, you can tell it's happening if you go anywhere near a typical layout with a radio and AM reception, it drowns pretty much. The other reason is that if you twist them, the amount of inductance, which relates to the amount of energy that gets stored in the wiring, goes down, and reducing inductance helps keep the DCC signal a lot cleaner. The other effect it has is if there's a sudden interruption in the current, like you lose contact with water for a very short time, the energy stored in that inductance tries to overcome that by spiking the voltage on the track, which is not good for decoders or anything else. You got to appreciate these aren't big issues, but they're there, and there's enough mysterious events can occur if you don't take some awareness of it. So that's when it starts getting a bit wild. You get advocates of you must twist it very tightly, and anything else is totally unacceptable, etc., etc. Well, that's all very well until you want to put a feeder wire on it. We have to be a little bit practical here. So I would suggest that a twist every foot or so is quite enough. Keep the other wires away, like in this picture I borrowed from a book here. The track bus wiring, and here's the control bus there. I don't know, 6-8 inches apart, that's fine. The other considerations are, the bus wiring is connected all the way along to the track, and the track in parallel is anything but an ideal configuration. It's definitely not twisted unless your track laying is really bad. So being fanatical doesn't help. I would suggest if you're making a long feeder run, 10 feet, 20 feet, yeah, you can twist the wires together a bit more. This one seems to attract fanatics about twisting the wire. I think it's very much been driven by the Cat5, Cat6 wiring and house wiring for Ethernet wires, very tightly twisted, and it's really important, but they're also working at 100 or 1,000 times the frequency that we're dealing with DCC. So these points do become critical. Even there, of course, you've got interruptions when they join a connector in the wall or so forth. So even there, being a little imperfect is still okay. All right, this is another great one. Snubbers or terminations and so forth on the electrical terminations on the end of the bus lines. I tried to come up with a really simple little analogy, good or bad, I'm not sure. There's this little toy known as Newton's cradle, because it illustrates one of the mechanical rules that Newton was so famous for discovering. But if you imagine the steel balls in these things are electrons, kind of big ones, carrying the DC signal along the bus that's collectively on the line they represent. So you bang the ball at one end, and a little bit later, the ball at the far end flies off. So, and then comes crashing back that and shoots the signal right back along the line of balls to the other end. Well, it's not quite the same thing, but more or less, that's what's happening if when the DCC signal reaches the open end of the bus line. How much it's happening depends on a lot of things, how much load is on the bus to absorb these reflected signals and so on. The electrical effects of this, you can get voltage spikes coming back that are twice the height of the original signal. And that's generally in excess of what decoders will stand for any length of time. So the idea of the snubber, so-called, is to absorb this energy that reaches the end of the line and the bus line and minimize or prevent even the electrical reflections that distort the DC signal and get voltage spikes, possible loss of control, and so forth. So why is it controversial? Well, it's very erratic as to whether it'll happen, depending on the exact wiring configuration of your layout. It usually doesn't show up detectable until the bus line gets maybe 20 or 30 feet. Why? That's because the signal is traveling along the bus line not quite at the speed of light, maybe half of it. Even 30 feet out and 30 feet back is a little bit of delay, and that delay distorts the signal that's on the bus. So depending on how the timing is and the exact length, it may make it momentarily go to a low voltage or a high voltage or oscillate between them. So we have the other thing. This is the manufacturers do choose to disagree vehemently. NCA recommend them, and they even sell a little gadget that I've shown here, which is nothing more than a capacitor and a resistor, so you can easily make your own. But they actually sell them as a recommended accessory, and they sell them in 2-packs, which probably is telling you they expect that you'll probably want to use them in several places. The end of any bus line or sub-bus. Digitrax, on the other hand, claim that their boosters are so wonderful that they control the bus signals very well and snubbers are never needed. Both statements are a bit extreme, but that's the reflection of why there's so much confusion. So I am going to make an opinion and say they work well. They recommend it even for smaller layouts. There's an awful lot more about this. 12 years ago now, DeVos published a 4 or 5 page article in what was then NMRA Scale Rails in 2008 on a whole lot of measurements taken with different boosters and different configurations of layout that was simulated. And the results are pretty startling. There's what snubbers do and what they don't. I wrote a sidebar a little more theoretically than here for that. Mark Gary's website has way more than you probably ever want to know, but that's up to date and goes on at quite some length. My suggestion is get them and use them. If you can solder even badly, they're very easy to make them yourself. Measuring the track voltage and maybe the current that's flowing in it. What do you want to know anyway? If the trains are slowing down or even speeding up in bits of the track, it's possibly even likely due to voltage differences on the track. At the extreme point, of course, there may be dead spots due to little bits of track that weren't connected to the bus, but relied on rail joiners that have now got a little bit old and corroded. A very important use is if you're having multiple boosters, one for each major piece of track arrangements, feeding their own buses. It is pretty important to get the DCC voltage levels of the different boosters matching to each other. It doesn't have to be precise to the nearest thousandth of a volt, but you don't want a big difference. It means when the train goes from the area powered by one booster to that powered by another, there'll be a big pulse of current that has to flow between them to make up the voltage difference. You might also want to monitor the current that the set of locomotives are taking from the booster. But the other thing, and this is where the discussions go on forever, how accurately do you really need to measure these? And I would suggest not very. What is more important is how repeatably you can measure a given value. Even when it comes to matching, for example, the DCC voltage levels of the boosters, if whatever meter or means you are using consistently gives the same reading, it doesn't really matter if it's a bit out. As long as you can match the two boosters, whether they're actually matched at 14 volts or 13.5, doesn't really matter. If the meter you're using just gives you the same value, the booster's the same voltage, that's enough. So a variety of tools can be used, and even the thing gets more. There's the famous ramp meter, which is a very cool toy. It can be used freestanding to pick up from the track, which will give only the voltage, of course, not the current, as you can see. It seems a bit cumbersome for that, but anyway, there you are. You can also panel mount it, in which case you can also then wire it to show the current being taken in a given block as well, if you want to do that. Then the next one shows a sort of mid-range, not the very fancy fluke ones, but a mid-range so-called true RMS meter. And what that means is that up to a point, it'll give a correct voltage reading regardless of the waveform it's looking at, and that hopefully includes DCC square waves. Really cheapo meters are calibrated for just the waveform of the standard power line, and that means that if you give them a different waveform like a DCC form, they may not read all that accurately. So that's good, but they're a bit overrated because I don't know if anyone will look up the specs on these things. Typically, they're really true RMS, or true independent of waveform, only up to maybe 1 or 2 kilohertz signal, and DCC signals are 5, 10 kilohertz and much higher. So they may be a little bit better, but it's not a magic cure-all to give you the precise reading on a DCC waveform. So at the other extreme, there's the Harbor Freight, often freebies meters. They are actually quite usable, which is handy. You can leave a couple lying around the layout if you need to do them, not have to go looking. They're actually tolerably accurate as well as repeatable, which is probably an accident of all the compromises rather than any designed-in feature. So it could change from year to year as the different models change a bit, as somebody engineers another few microcents or micro yuan out of the cost. But at least the ones I have been quite surprisingly accurate. So it's quite usable. Main problem is that it's only got 2 AC voltage ranges, and the lowest one's 200 volts. So you don't get a very precise measurement. You can read 12.0 or 12.5, but no closer. This is not generally available, but I made up a little box with a little DCC to DC converting circuit in it to just keep semi-permanently on one of these meters, and it makes it rather nice. Now you can use it on the DC volt range at 20 volts, got lots of precision, and make a really good measurement. It's actually, by the switch there, actually enables me to look at the average DCC voltage or the peak. And the point about that is if there's very much difference difference in them, it means we've got spikes on the DCC signal like we were talking about a minute ago. So if you're just looking for dead spots that aren't powered in the track, I find nothing more handy than an automobile wire test light bulb. As shown here, they're about $5, which is also a good point. The other advantage is, as long as you can still get them with little incandescent lamps, 12-volt lamps, they put a little bit of a load on the track, like there was at least a lighted coach there or a small locomotive. So it's a lot more realistic test of whether the track really is dead or not. You just put a meter on it, even the slightest leakage will tend to give you the full voltage reading, but there could be so much resistance. As soon as there's any current being drawn, you don't have it anymore. The auto test lamp does that. So a very handy thing to have on hand at all times. That's the main ones, but I pick up on a couple of other topics. If you have any inclination at some point, you might want to be into detecting the presence or even and location of the trains or signaling. The power districts could be usefully split up into even smaller local blocks with the current detector feeding in it, such as in the previous slide. You have to be a bit careful where you put them, because if they're, as it were, upstream, in other words, between the bus line and a juicer being fed, those frog juices take a little bit of current and they'll make the detector think there's something on the track, whether there is or not. But again, there's lots of instructions about that. There was, for we're going assuming forever, the so-called configuration of the turnouts. It seems to have settled down to the main point being so-called live frogs or insulated frogs, sometimes known as inchful frogs. I have a whole mixture on my layout because it's been going on for a long time, but I'm more and more regarding the insulated frogs as a little bit of a train set, if you like, hangover. It's still usable, but it doesn't look so good, and it's really not the best arrangement for contact with the locomotive. Live frogs, of course, you got to switch them to suit the route that the train's taking, which is where the frog juices or the switches on a tortoise machine or similar come in, but suggested for all new work. Then there was the still slightly ongoing, the DCC friendly, or otherwise. The guy who runs the wiring for DCC site claims to have invented this term. He might well have. But where this came up originally was the older type, many of the older type of turnouts where the switch blades would have a metal tie bar between them for moving them together. Consequently, they were electrically connected to each other. Now, if they were perfectly to gauge and all wheel sets were perfectly to gauge, it was sort of okay. But if not, you tended to get a case where the back of a wheel would brush against the open point and cause a momentary short circuit. And with DCC, sort of okay. But for all the reasons we mentioned, a DCC breaker needs to react really fast and trip. So it will, and you get a shutdown. So what we might call old school turnouts, like the older Shinohara or Walters ones, I'd say not a good thing to reuse for new DCC layouts. There were a whole lot of instructions about how you could convert them, which were very damaging and relied on solder joints and moving parts, which really is not a good idea for reliability. So some of the other normal wiring reversing loops, they're pretty much thoroughly covered in the reference books. So I made a really quick table that just suggestive, and it's based around perhaps HO or for many of the audience, S narrow gauge, much the same. But if you sort of look at small, medium, and large layouts, these are kind of what you'd expect to be aiming for in a build. I don't have to do them all at once, but These are the suggested planning levels. So what I've said there, the area, what I've called small, medium, or large, it's a sort of very arm wavy thing. It means sort of 100 square feet room, not so much 100 square feet or 200 square feet of layout surface, if you like. Typically that would be 60%, 65% of the room area if you try and pack it without getting to excess. The very large layouts, I put it, but it's really outside the scope here. They're so individualistic that you have to plan them individually as well. And also thought it'd be worthwhile just finally recycling some of the summary from 16 years ago, different from what people were accustomed to, but I think now are much more familiar, DCC wiring. There's much higher currents, so you need the overload protection and the heavier wiring. And I've emphasized this several times, but one more time. It's really intolerant of sloppy workmanship because the resistance of the joints will go up and it won't shut down properly. And if you have multiple locomotives drawing a lot of current on one area, they'll all slow down if they don't lose control. Turnouts used to need a lot of attention for trouble-free operation. Now, ones on the market, it's pretty much plug and play. You might have to add or remove a link underneath the turnout to the manufacturer's instructions, and that's about it. So if you need any more, then I offer you the originalist reference in this whole topic, going back 70 years originally. There may even been an earlier version. Still got a lot of interesting stuff in it, but it's amazing, perhaps not so amazing. It's amusing almost how much things have changed. And the tobacco pipe is no longer required. I would say, apart from health reasons, even undesirable near the modern electronics. They don't like getting contaminated. So I thank you very much. And hopefully this hasn't gone on too long. So give it back to you, Alex. And if there's any questions that I'll be happy, we can connect later if you like.
Okay, well, thank you very much, Max. That was a tremendously informative clinic. I really enjoyed it personally. A question for you, Max. Would it be possible for you to make your slides available to people if they wanted them?
Yes, I can try and get them on the 4D website too. Not just the YouTube presentation, but the actual slides.
That would be really great.
The previous, the 2004 set are still there after all this time. So that would be a good compliment.
Max, I've got a question for you. One that I've been deciding whether or not to do that on my layout, since I'm about to embark on the wiring journey. I'm planning on using stranded wire. When you say if you use something like a Waco connector, where you have a terminal that you push the wire into and then screw it down to lock it in place, do you recommend tinning the stranded wire first or just put it in, maybe just hand twist it?
I don't think it makes much difference. If you tin it, the only issue is that the solder will flow in between the strands, making them in effect a solid wire. And consequently, that goes inside the terminal. It's clamped. In the Wago case, it's not screw clamped. There's a little bar comes down and pushes on the wire when you push the lever down. And then if it gets wriggled, it'll tend to fracture at the point where the solid wire goes back into becoming stranded. It might be better just to twist the strands together and stay with that.
Okay.
But I made the point, those other blocks that do have the white blocks that have screws into the metal piece that the wire goes into, it really is important not to use ones that just have the screw, but ones that have the little plate in there as well to push down on the wire, particularly with stranded wire, because the screw will sort of chew right through it.
All right, Maxwell, thank you very much. That was an outstanding clinic. It really was. Okay, but that's about it. We'll see everybody later. Bye bye.